Hello, I'm Anna Mackay, and today I'm going to do my best to explain standard deviation and variance to you here. I'm going to explain it in the basic form before we necessarily adapt it to the topic that we're doing in terms of the discrete random variables, in terms of having probabilities and stuff like that. Okay, so here are some of the formula, and we're going to come back to them. Handy to jot down. I'll explain them in a bit more detail. I'm going to take you back to an example from a Year 11 textbook. This helps me understand where standard variation comes from in a visual kind of way. So to summarise this example here, we're just going to look at the first row. So imagine that we have 5 random samples, hence those 5 numbers there, of 40 oranges, and we're looking for blemishes. And so the number of blemishes of each of those sets of 40 are these 4, 16, 14, 8 and 8. All right. So we're going to look at trying to find the standard deviation for that. We're just going to do one. So the formula for that, well, involves the mean. So first of all, our mean is you add them all up, and there's the total, and divide by how many's there, and we have 10. Just taking that now, the formula, the official formula for standard deviation is this. Now compare that to what we're doing in the topic that we've got at the moment. You can see the similarities. You're taking each value and subtracting off the mean and squaring that. And you want the sum of all of that. That's the same both times, and there's the square root. And one of them's got the probabilities, and the other one divides by how many are there. So we're just going to look at this one first. All right, so to do that part of the formula, what you have to do is you have to take each item, and so these are the number of blemishes on, or how many oranges that had blemishes out of sets of 40. And for the purposes of this, we're going to assume this is a population. We're not going to look at it in terms of a sample. And so you look at the distance in theory from the mean each time. So you take each number and subtract off the mean. So here we have 4, and we're going to subtract off that 10, and that gives us -6. You have 16 blemishes, and you subtract off the average, which is 10, so it's 6. So that's +6 because it's that's more than the average. This was -6 because it's less than the average, and you go on and do that. Now if you add all of them up, you might refer to this as the variance, by the way. It's 0. So what that could say is that, well, if you look at all of the ones that have more blemishes and all of the ones that have less, how much do they vary? Well, it's a 0, which is sort of implying that there is no difference from the mean. And so you can see the problem here, that because we've got the distances for some of them as negative, the distance from the mean, it's possible to get a 0 variance, or how much they vary. So this is part of the reason why we square this number. So as you can see, part of this formula here, it's got that square. So it's the sum of the squares. So going back here, that means we take each of these numbers and square it to make it positive. So that reduces the negative factor. And part of the square root is to cancel out that square. That's part of it. So you can see we've squared each of the numbers here, right? -2 squared is 4. And we get 96. All right, now I want to create a bit of a visual for you. So, a bit of a graph here. Don't have to draw this, just want you to try and understand it. That if we had a scale here of 4, a scale up to 16, and our mean is 10, as we know, let's plot each of these 5 sets of blemishes for oranges onto this graph. So we've plot all 5 of those scenarios on, and let's think about what the distance is from the mean for each of those. So the distance from the mean down to 4 is there, and then here's all the distances. And as we saw before, those distances averaged out to be, well, not average, that's not quite the right word, but because some were below and some were above, overall it was a difference of 0. So what we're actually looking at is the variation of each point from the mean. And we're going to look, the standard deviation is essentially the average of those differences. And it actually comes from, this is my understanding, I might not be completely right, but this is how I've come to understand it by trying to unpack it further to do this video. It comes from the distance formula, it comes from Pythagoras. So if you want the distance between 2 points, so you've got one point here of the mean of 10 and the other point here as the point of 16. How would you find the distance between those 2 points? So traditionally, you might have a right-angled triangle, and you use Pythagoras' theorem to find the distance there. And that's how we get the distance formula, which is, so there's our distance formula there. Now let's go back to thinking about these 2 points. If they were coordinates, what would their points be? Well, let's just say they were the second point along, so their x value for the mean here would be 2, and it's 10 up. And the other point here, it's also the second point along, and it is 16 up. So if you were to substitute that into the distance formula, those x values are the same, 2 and 2. So 2 take 2 would give you 0, so that whole term has disappeared. So you're only left with this part of the formula here, which let's write that out. You might already be able to see some connections between the standard deviation formula that had a subtract here, it had a square and a square root. So this is the formula for just one point. So that's how we would calculate the distance between these 2 points, the 16 and the mean of 10. So you could probably see now that, let's see if I've got it on the next slide. Our standard deviation formula here is that this part of the formula is you're taking each point and you're looking at its difference from the mean, and we're squaring that because that square comes from the distance formula, and hence that square root at the end counterbalances that. That's how you, I guess, undo the square that would have been on the hypotenuse, so to speak. But we're looking at the average because we want the sum of all of these. So that means all of these numbers here divided by how many's there. That will give us our standard deviation. That might all be a little bit much for now. It might be something that you think about and you come back and re-watch this and rethink about it for yourself. Or if you were to even explain it to another person yourself, that would condense it in your mind even more. So how do we work out this formula? The numerator is that 96, so that was the sum of all the squares, divided by 5 because there were 5 terms there, and we take the square root of that. And therefore under the square root sign is 19.2, and we get 4.38 for our standard deviation. And just noting, what is the variance? The variance is that number under the square root, or you could take the standard deviation number and square it. So variance is the average of squared deviations. So I guess the variance is, when I drew that diagram before like this and you had your mean, the variance is how much things vary from the mean, and I guess the distances overall, whereas the standard deviation looks at that average of all of those distances. So 4.38 from a mean of 10, that, well, I guess what I'm saying is the smaller the standard deviation number, what could you say about that data set? The less it varies. So the closer the numbers are clustered around the mean, and the bigger that standard deviation number, and therefore by default the bigger the variance, the more spread out those numbers are, because it's about the distance each of them are away from that mean number each time. And the units for variance is in squared, and we'll come back to that in another video. I think it's the next one, when we look at why we therefore take standard deviation more often as opposed to variance. Here's a table that I found on the internet that might be of some use. Feel free to pause and have a read through. The things I found the most interesting is that at the bottom here, the variance indicates how far individuals in a group are spread out. So in terms of those oranges, thinking about how far away each of them were from the mean. And the standard deviation is how much observations of a data set differ from the mean. So sort of all up. Okay, and a quick example here in terms of the topic that we're in for our Year 12 maths here, putting it into a probability type of question here. So a fair die is rolled and has the following probabilities. This is to be expected. And then we're going to calculate the mean, which is the expected value. How do you do that? So using your graphics calculator, you put in the x values in list 1, and in list 2 you put the probabilities. So this is 1 divided by 6, or 1 over 6. Then you need to calculate that, so we're using our F2 button here. You need to make sure that it's not just got the 1 here. You need it to be referencing list 2, because it's taking each of those numbers and multiplying it by its probability for its frequency. And you'll get this calculation. So what is this? The 3.5 is your expected value. So you would write that here. So that's your average of what you expect to happen. Now, you can never roll 3.5, but what it's saying is that if you conducted this over time and looked what your average would be, it would be 3.5. The standard deviation, as you can see here from the screenshot, is 1.71, let's put. And how to calculate variance, you square that number. You take that 1.71 and you square it, so you get 2.917. So even if a question actually asks you Part B's variance first and then standard deviation, if you use your graphics calculator, my advice is work out the standard deviation first and then go back and square that number using your run mode. Just comparing this to what we talked about earlier in the video, these are the two formulas here. So what your calculator is actually doing is, when we got that 1.71 for the standard deviation, this is the formula it's using to calculate that 1.71. I'm just going to show you quickly by hand how that would happen. And notice the similarities here. So we've got the sum, adding them all up, the square root, the square, but this time around instead of n, you have to take into account the probabilities, which is how often each of those things happen. And doing that by hand is here. So we would have an enormous square root sign here, and you start by taking one x number and subtract off the mean. So we have 1 and we subtract off the mean, which was 3.5, so the expected value, square that and then times it by the probability of that one happening, which is a 6. Do it for the next number and so on. So that's how that formula is written out by hand, and that gives you the answer of that 1.708 or that 1.71. So this is showing you what your calculator is doing to get that number. Okay, thank you for joining with me. See the next video, 7E, properties of AX plus B. Thank you.